Okay, let's get started with today's session. So, welcome everyone to week 8 of the course Optical Spectroscopy and Microscopy Fundamentals of Optical Measurements and Instrumentation. So, I am Arjun, and as usual, as I have been for the past 7 weeks, I am the TA for this course. And welcome everyone to week 8's TA session of this course. So, we are almost two-third done with the course, and so the routine for this TA session will be similar to that of the previous 7 weeks. I'll be going over a brief weekly recap of what happened, a weekly recap of what happened in the course lectures of the session, and following by that we'll discuss some sample problems which I have curated, and after that we'll be discussing the past week's assignments. So in till the last week we have discussed 6 weeks of assignment problems. So in this week today we will be discussing about week 7's assignment problems. So I'm not able to see anyone in this room, so I'll just get started with the recap of. One second. Yeah. Yeah. So in the past 7 weeks of the lectures, we were seeing about processes such as um, we were so from the beginning of the course we were looking at processes, quantum mechanical processes that will explain optical phenomena, and we were slowly seeing how processes such as absorption, fluorescence, and phosphorescence came into existence, and how we are able to explain them using quantum mechanics. And slowly we built upon those quantum mechanical equations to kind of describe come at semi-quantitative ways to explain how things work in optical instruments and instrumentation processes, such as how your laser works and how your superfast laser works, and how the lasers can be tuned or adjusted or worked in such a way that it will be suitable for any applications that we are going to work on, which will be a microscope in return. So till the last week, I think in week 7 we were looking at till week 6 we were looking at continuous wave lasers, and in week 7 we started looking at pulsed wave lasers, where we looked at the two important processes that are used to carry out the process of pulsing, mainly Q switching and mode locking. So uh, we kind of very vastly went over the process of Q switching, and we slightly touched upon the process of mode locking, and where we actually left off in the past week. And in this week 8 lectures, what we basically did is we kind of extrapolated, kind of carried forward from the concepts of week 7, that is Q switching and mode locking. We actually saw how mode locking and all those processes work. So we started off by discussing how many nodes a certain pulse width laser can withhold, which depends on your specific bandwidth of the laser as well as your spacing between your nodes. And after that, we looked at um, uh, several types of Q switching as well as mode locking as well, where we looked upon your active Q switching and as well as passive Q switching, where your active switching involves the use of acousto-optic modulators, and your passive pulse laser module depends on the use of your saturable absorbers, which selectively uh, transmits or alters your low loss situation. So we also looked at other concepts such as your Kerr lens mode locking and mode locking format, and we saw how refractive index helps in like aids in refractive index of a medium helps in modulating the resulting intensity, and how we saw that the refractive index process as a own, like the physical property of the refractive index on own, is independent of the intensity, but rather it just influences the resultant intensity coming out of the laser. And we were able to see how those processes were helped to design prism filters, which we saw at the later parts of the course. And we also went over other processes such as pulse compression and how pulse compression happened. And we also saw a demo of how a laser works. Basically, we saw a titanium sapphire laser works. We saw all the instrumentation components present there, where we also saw something called as a prism pair compressor unit, where we had four prisms and how the width between two consecutive prisms helps us modulate the delay between different components of light. When we have visible light in VGR form, how the width between the prism units helps us delay modulate the phase differences between light components of the cell, and how individual modulation of each prism component helps us either delay the different components of light or increase or decrease the spread of different components of light. And towards the end of the week's lectures, we also touched upon minor concepts from Gaussian beam optics, where we saw how the resultant intensity of the light varies with the incident intensity depending on certain parameters, what we call as the uh, waist width, the beam waist, which is the resultant thinning of the beam diameter, which will not be actually a point object but rather than a spreaded object, and it will also depend on the distance of the object from the lens. And we also saw how the addition of different lenses helps in modulating the resultant intensity of the light. We also saw how collimated beams are formed, how collimated beam is managed to retain about 87% of the light intensity which is incident on a lens. And we also saw several relationships about how to measure your Rayleigh range. Basically, your Rayleigh range is the range as the distance at which your waist width is measurable by a factor of Wz is lesser than or equal to root 2 times of W naught, omega naught. And we also saw how these concepts of Rayleigh range as well as your Gaussian beam optics can be extrapolated to concepts such as telescope as well as microscope. So these were the basic concepts that were taught in week 8. So we can have a short doubt session where we can discuss about this concepts. Um, if I can have time till now the time is 3:13, we can have time till 3:20 to discuss about the general doubts in this session. If any of you have anything, else we can move on to solve the uh, sample problems that I have curated for this week. Okay, if there are no doubts, we'll get started with the sample problems. So, what is the question number one? What is the primary limitation of using imaging sensors like CMOS to measure the width of a small laser beam? So, what is the primary limitation of using imaging sensors like CMOS to measure the width of a small laser beam? So, options are low dynamic range, coarse sampling due to fixed pixel size, typically 4 or 5 microns, spectral mismatch, or overheating of the sensor. So this will be coming in the last section of your last lecture of your week's lectures, where we saw that there are two types of imaging sensors, CMOS and this razor blades. And your CMOS gives you uh, CMOS can't help you measure small laser beam widths due to sampling sizes, pixel sizes, and therefore we proceed to use razor blades. So the option here, correct option here is option B, coarse sampling due to fixed pixel sizes, typically 4 or 5 microns. Question number two, which mathematical function describes the integrated intensity profile obtained when moving a laser blade across a Gaussian laser beam? So, which mathematical function describes the integrated intensity profile obtained when moving a laser blade across a Gaussian laser beam? Sorry, excuse me. So the options are parabolic function, Lorentzian function, error function, and sinus function. I mean, I left the question. Sorry. One second. Sorry, yeah. So yeah, I just intentionally left the question like this because it will be easier for you to calculate the answer. So basically, we just saw one function in the week, 8 lectures, which is like the easier way to go around this question, which is error function. But basically, one second. But basically, your error function is like your error function describes the intensity profile when you move a laser blade across a Gaussian laser beam. Yeah, so that's where your Gaussian optics come in, and your error function also comes in. So question number three, in a standard two mirror alignment setup, what is the specific role of the first mirror? In a standard two mirror alignment setup, what is the specific role of the first mirror? So So in the prism controller, we saw that initially there will be four lasers, and the incident light on the first prism is dependent on the mirror alignment setup, where we can see that the mirror should be aligned in tandem with the prism, so that the angle at which the laser is incident upon the prism can be controlled. So only if the angle is controlled, then we can get the desired spread or of the components of light, or we can get the desired width of the components of the light in whichever order. So the correct option here is option B, where your first mirror controls the slope or the angle of the beam. So option 4, I think this is pretty simple. How is the optical axis of the system defined? What is basically the optical axis of the system? So whether it's the path of the most intense light in the room, whether it's the geometric line connecting the centers of the lenses in the setup, whether it's the normal vector to the laser head, or it is defined by the polarization of the light source. So we all know that all the lenses or all the uh, all the lenses will have something called as the optical center, and there will be a line connecting the all the centers to indicate the center of the lenses, and that line is basically the optical axis. So the correct option is option B. So optical axis is a geometric line connecting the centers of the lenses in the setup. Last question. So it's a numerical problem. So a laser beam follows a Gaussian intensity distribution. So we all saw the Gaussian optics where you have the relationship, which is where your IR is equal to I naught e power minus 2 r square by omega naught square, where your R is your yeah. So where your omega naught is your beam waist and r is your distance of the object from the center of the beam. So here what we have mentioned is we have mentioned that your I naught is we have mentioned your I naught. We have mentioned your beam waist the omega naught, which is 200, and we have also mentioned your r, which is 100. So I'm asking you to calculate I of r using this relationship. So all you need to do is substitute and find the answer. And since no one is in the room, I'll just proceed to give the answer. So basically, we have given the relationship to you. I've given the relationship to you through this expression. IR is equal to I naught into e power minus 2r square by omega naught square. So we have I naught, we have r, and we have omega. So we just need to substitute that, and by substituting it, you will get this expression. And upon solving it using the calculator, you will get the answer as IR is equal to 6.07 milliwatt per millimeter square. So I hope this problem is clear. Once again, I can explain it again. So we have this Gaussian intensity distribution where IR is given by I naught into e power minus 2r square by omega naught square, where we have your IR, which is your 100, and where we have your omega naught, which is 200. So basically, you just have to substitute all these values I naught, R, and omega, and you will get this mathematical expression. And you just have to solve it in the calculator to get the value as 6.07. Since the I naught is already in milliwatt per millimeter square, uh, here the I naught is already 10 milliwatt per millimeter square. So I'm also asking you the answer IR in milliwatt per millimeter square. So the final answer will be 6.07 milliwatt per millimeter square, which is what you have to type it. So that's all the sample problems I have for this today from week 8. So can have further doubt session to discuss the problems that we have discussed so far. So if there are any doubts, you can ask. Else we can go on to discuss the week 7's sample, week 7's assignment problems. Okay, then let's discuss the assignment problems. So the intensity of a signal is directly proportional to square of the incident intensity. What will be the ratio of the signal when elicited by laser beam with M00 mode to that of M01 mode laser beam with same power? So they're just basically asking that 1000 to 1001 will be the same ratio. So we already know that 1000 to 1001 will be the power of the laser will be like around 8 times or something more than that. And they're saying that the intensity will be square of that. So if you do all those calculations, you'll get the ratio of 1000 to 1001 as 2:1. So given at a time t0, t is equal to 0, the pump is turned off and the population difference between the lasing levels is 1000. Estimate the number of round trips the beam will have to make before it depletes the population difference. So they're saying that time is equal to 0, the population difference is 1000. And we all know that the average time it takes for, so not average time. So every time the pump is makes a round trip, every time the beam has to make a round trip, the population is kind of decreased by half. Population difference is kind of decreased by half. So basically, how much trips it needs to uh, make the population difference as 1000. So it will be around 10 trips because 2 power 10 is 1024. So by the time your population difference would be uh, gone, like depleted. So the answer would be 10 trips. So given that the cavity length is 1 meter in this question, what would be the approximate pulse duration? So we know that this from week 7's formula, we know that the mode spacing lambda delta mu is given by c by 2l. So if you want to find the pulse duration, you just have to flip the parameters over. So to find the pulse duration tau p, it will be 2l by c. So you just have to multiply 2 into l, which is 1 meter in this question, and divided by the speed of light. So if you do that, you will get the answer as approximately 60 nanoseconds. Question number 4, it's a pretty direct question. So what happens when the light passes through a saturable absorber and the intensity is below the saturation? So when you involve a saturable absorber, it just means that if it's not if it's not saturated, then it just means that it absorbs regularly. So the answer will be regular absorption. And another direct question. So Pockels cell is used for what? So it's a multiple select question. Pockels cell is used for your fast switching as well in your Q switching as well as your altering polarization. So the answers will be options A and B, which is your fast switching and altering polarization. So given the cavity length of a laser cavity is 1 meter, calculate the mode separation for laser operating with the center wavelength of 900 nanometer. So for this, you need to use the formula. So the formula will be mode separation is delta lambda. So they are asking mode separation in nanometer, not in frequency. So mode separation in delta lambda will be lambda square, lambda c square divided by 2l, where lambda c is your central wavelength, which is 900 nanometer, divided by 2l, where l is your length of your cavity laser, which is your 1 meter. So if you do that, it will be 900 nanometer square divided by, sorry, uh, uh, sorry, yeah, lambda c square by 2l. Lambda c square by 2l. So if you do that, you will get the answer as approximately 40 into 10 power minus 5 nanometer. So just to give an annotation, it will be so both of them are 10 power minus 9, so it will be 10 power minus 18. If you divide it by 1 meter, sorry, 2L, so it will be 2 into 1. So 9 into 9 is 81. 81 by 2 is 40.5. 40.5. There are 10 power 4. We have 10 power 4 here. Out of this 10 power 18, if you have 10 power 4, you will have 10 power minus 14 left. So out of that, you can make 10 power minus 14 as 10 power minus 9 into 10 power minus 5. So your 10 power minus 9 will be part of your nanometer calculation. So you will have 40.5 into 10 power minus 5 nanometer. Yeah. Given a square pulse train of pulse width 100 femtosecond, repetition rate of 100 megahertz, the average power of the laser is average power of the laser in 1 watt. Calculate the peak power. So they're given the average power, and then they're given the repetition rate, and then they're given the pulse width. So with that, you have to calculate the peak power in watts. How will you go around solving it? So from the average power, so we have the average power. So you have to find the total power. So how you find the total power is basically you find the you multiply the average power into with the repetition rate. So with that you will get the total power, and then with the when having the total power you have to give the pulse width, and then from the pulse width, if you divide it by the pulse width, you will find the peak power. So if we do all that, we'll get the answer as 100 kilowatt or 10 power 5 watt. So the next question, find out the number of photons emitted from 1 milliwatt of 532 nanometer light in a second. So basically we have wavelength, and basically we have the power. So how will you go around finding the number of photons? So basically what we need is number of photons. So for that what we need to do is first we need to calculate the energy using the 532 nanometer light. So once again, how we do this, we use this formula E is equal to hc by lambda. We already know h, we already know c, and we already know lambda, which is given by 530 nanometer. So we substitute this to find the energy, and then we already have the power, which is 1 milliwatt. So the number of photons is basically your power by energy, which will give you the number of photons. And if we do all those calculations, you will get the final answer as 2.64 into 10 to the power, one second, 2.64 into 10 to the power 15 photons. So I hope people are clear with this. This is a direct question. Wavelength of operation of Indiag, Ruby and helium neon laser. So we already know Indiag operates in 1064 nanometer. So there will be no other option for this rather than option D, where Nd:YAG is 1064 nanometer, Ruby is 694 nanometer, and helium neon is 632 nanometer. The last question is the length of the grating element generated by pressure waves generated in medium with velocity of 300 meters per second at 25 kilohertz is given by how much? So it's simple. So you just divide the velocity by the frequency. So upon doing that, you will get the answer as 12 nanometer. Option A, 300 by 25. So 300 meters per second divided by 25 kilohertz. After doing that, you have to calculate convert the answer in meters to millimeter. So upon doing that, you will get 12 millimeters answer. So that's all the assignment solutions for week 7. So since we discussed week 8 today, I can't discuss week 8's answers today. We'll be discussing that in the next week. So by the time, if till then we have some more time left for the session to get over. So if anyone has any doubts, they can shoot out. Else, we will. I thank you all for coming for today's session. We'll see you in next week, next Sunday, 22nd March, from 3 p.m. to 5 p.m. So where the in that session we'll be discussing about week 9's course content and sample problems and week 8's assignment solutions. So till then, if anyone has any doubts, the room will be open for that, so that people can answer, ask their questions. So if no one else has any doubts, we'll meet on 22nd March from 3 p.m. to 5 p.m. Thank you.